as we've seen, our enantiomers are molecules that have the exact same atoms and the exact same bonds between our atoms, but a different spatial positioning of those atoms relative to one another. So enantiomers, of course, are specifically mirror images, such as the two molecules that I'm showing here. And although they're perfect mirror images of each other, no matter how we reorient them, we can't get them to completely overlap or superimpose on one another. So they're actually unique molecules with unique shapes. Now, with these molecular models, of course, it's very easy for me to look at them and see that, yes, they do have different shapes. But if we're talking about real molecules, they're incredibly tiny, and so we can't just look at our molecules and say, oh, that's an R enantiomer, or that's an S enantiomer. So we need a way of measuring what enantiomers we have so that we can distinguish between these enantiomers. And again, as we've learned, those enantiomers might have different biological effects just from the difference in shape, and then how that shape might fit into the shapes of other molecules in our biological systems. In order to measure our enantiomers, we're going to use polarimetry. So since enantiomers have the same atoms, they're usually going to be very similar in terms of many of their physical properties. They're going to have the same melting points, the same boiling points, because they essentially have very similar structures, as we've seen. Now, polarimetry is going to use a slightly different property of our compounds, which is whether they are optically active and how they interact with our light. So before we can understand this, we first have to take a look at our light. So light is a wave, so we can represent it using a sine wave like I've drawn here. So this wave right now is oscillating up and down. But for most light that we see normally, things like the light from lamps, that light is unpolarized. And what that means is that it's actually oscillating in many different directions at the same time, not just up and down. So rather than just showing one wave going up and down, we really need to draw other waves at the same time, oscillating in different directions. So I might have a wave that's going out towards you, and then coming back towards me, going back towards you, going out towards me, moving in this sideways direction. So it's oscillating side to side instead of up and down. And our unpolarized light is actually made from this light oscillating in all directions at 360 degrees. So imagine hundreds of other waves pointing in all different directions, all combined together as this unpolarized light. Now, with our polarimeter, what we're going to do is we're going to take this unpolarized light and we're going to filter it to make polarized light. So we take this light and we pass it through our little filter, which is just going to block out all the waves that are oscillating in different directions, except for our one wave that's just oscillating in one direction. So we just have our up and down oscillating light wave. Once we have our polarized light, we're going to shine our light into our sample with our organic molecules. And when that sees our chiral asymmetrical molecules, those molecules are actually going to interact with our light, and they're going to rotate the direction that this light is oscillating. They're going to rotate the polarization of our light. So it's going to be oscillating up and down. It's going to hit our molecules, and it's going to rotate so it's oscillating kind of at a diagonal, where it's not quite up and down, but not horizontal either. Now, as it's being rotated, so this is our optical rotation, and our molecules that rotate our polarized light are, again, optically active or chiral molecules. The amount of our optical rotation is going to be affected by a couple key parameters. So we're going to represent this using an equation. We have our optical rotation represented with the Greek letter alpha. This is going to be affected first by what kind of molecules we have. So this symbol here, our alpha in brackets, represents our specific rotation. So specific rotation is constant for a given molecule, and it just tells us, based on the structure of that molecule, how much does it rotate the light. Some molecules will have a large effect on the light, some will have a very small effect on our light. So this is unique for a given molecule, although you may have some molecules that might end up with very similar specific rotations. Now, of course, if each molecule is rotating our light, the next thing that should affect our overall optical rotation is how many molecules we're running into with our light. So we can tell that using our concentration. So concentration tells us the number of molecules in a given volume. So if we're hitting a lot of molecules, each of those molecules is going to rotate our light a little bit, and so we're going to see a very large optical rotation overall. Now, concentration is based on volume. So we also need a measure of how much volume we're going through as well. So this is our path length, which is represented with L in our equation, lowercase l. And that just tells us how much of our solution is our light passing through. If it's passing through a lot of solution, it's going to hit a lot of molecules and see more rotation overall. If it's just passing through a little bit of solution, then you'll only see a little bit of optical rotation. So these three key parameters will affect the overall optical rotation that we see. And we can actually use these then to determine our other parameters, right? So if we know the concentration and the path length, those are fairly easy to determine. We can then measure the specific rotation if we see what our optical rotation is. And that would tell us something about our molecule, right? We can match the specific rotation to the specific rotation of a known enantiomer, and that can tell us what molecule we have in our solution. Now, the first thing that we need to... Now, one of the important things to know here about our specific rotation is that it's actually going to be unique for specific enantiomers as well, right? So we know that we can identify our enantiomers as either R or S, and you always have a pair. You have an R, and then the S enantiomer is the mirror image of your R enantiomer, and their specific rotations will actually be related. So the specific rotation of our R enantiomer is going to be the opposite of the specific rotation of our S enantiomer. So whatever direction the R rotates it in, the S will rotate in the opposite direction. Right? They each have the same structure, just one mirror image is right-handed, the other is left-handed, and they rotate in different directions. So we can use this fact to help us determine which of our enantiomers we have. Right? If we know that the R enantiomer rotates light in the positive direction, which would normally be clockwise, then we know that the S enantiomer would rotate in the negative direction or counterclockwise. Or if our R enantiomer rotates in the counterclockwise direction, our S enantiomer would have to rotate in the positive or clockwise direction. They're always rotating in the opposite direction from each other. Now, in many cases, though, we're not going to have just one enantiomer. So we'll often have mixtures of enantiomers, and in this case, we need to know what the enantiomeric excess of a specific enantiomer is. So we use a separate equation to calculate the enantiomeric excess. The enantiomeric excess is just defined as the percentage more of one enantiomer compared to the other. So if we're specifically looking at the enantiomeric excess of the R enantiomer, we would take the amount of our R enantiomer, subtract the amount of our S enantiomer, and divide that by the total amount of our enantiomers. Right? So just looking at the percentage difference between our enantiomers. And then you would rotate this by 100, multiply this by 100% to get the percentage. Now, since our enantiomers are both rotating in different directions, our overall specific rotation for this mixture is going to be based on the competition between our two different enantiomers rotating in different directions. Right? If you have all R, it might rotate in this direction, but then as you add more S, that rotation is going to be decreased by the competing molecules of our S enantiomer. So we can look at the specific rotation of our mixture, and it's going to be based on the specific rotation of our enantiomer times the enantiomeric excess of that particular enantiomer. Right? So if we have 100% R, then the enantiomeric excess of our mixture, of course, is equal to the so if we have 100% enantiomeric excess of our R enantiomer, then our specific rotation of our mixture, of course, would be equal to the specific rotation of our R enantiomer. As we increase the S characteristic, the percentage of our S enantiomer, then that's going to decrease our excess here and decrease the overall specific rotation. So again, that's showing the competition between our two different enantiomers, where they're basically both rotating in different directions and competing against one another to determine our overall specific rotation, which of course will also determine what our optical rotation is. In order to understand what the specific rotation of a mixture looks like, it's helpful to look at this in graph form. In this case, we're going to look at an example of an enantiomer with the specific rotation for our R enantiomer of plus 10. So that means that if we have 100% of our R enantiomer, so we only have our R enantiomer, so our specific rotation should be plus 10. So we start out up here at plus 10, and then as we increase the amount of S enantiomer, or decrease our enantiomeric excess of the R, this is going to decrease, right? Because we're going to have some molecules that are rotating in the negative direction and some that are rotating in the positive direction. So our specific rotation for the mixture decreases. We decrease, we decrease, we decrease. And then at some point we'll have an equal amount of both our R and our S enantiomer. At that point, half our molecules are rotating in one direction and half are rotating in the opposite direction. The result is that we have no rotation overall, right? They're just canceling each other out. We refer to this as a racemic mixture. A racemic mixture essentially acts as if there are no enantiomers. All the enantiomers are kind of canceling each other out, and at least from our polarimetry perspective, we can't tell that we have any enantiomers. Now, some of those enantiomers might be having biological effects, others might not, based on their shapes. But from our polarimetry perspective, we can't tell the difference. So this can be kind of a dangerous spot to be, because it looks like we don't have any chiral compounds that are rotating our polarized light, but we actually have two different compounds that are rotating in opposite directions. So at this point, we've reached 0 on our enantiomeric excess of the R, and so at this point, we're essentially looking at the enantiomeric excess of the S. Right, so this is now going to be going to 100% of the S. So we'd say it's negative 100% R or positive 100% S. So we're switching, and now as the S is increasing, we're going to be rotating in the negative direction. Right, so remember, our R and our S enantiomer always rotate in equal and opposite directions. So if our R enantiomer rotates plus 10, our S enantiomer would rotate minus 10. As we increase the amount of S enantiomer, this will increase until we get to minus 10 when we have pure S enantiomer. As we change that excess, we're always going to be somewhere in between these 2 points. So we can be at most plus 10, at lowest minus 10, and somewhere in between if we have a mixture of both of these. So as we see here, polarimetry is a very valuable tool to measure our enantiomers. We can actually use this rotation of polarized light to tell us something about what enantiomers we have, right? So the specific rotation is unique to certain molecules, We can also learn about what our overall mix is of the R versus the S enantiomer, since they both rotate in different directions. We could even see if we have a pure enantiomer versus a mixture of enantiomers, just based on how much our light is rotated. This is, again, is very important in our biological scenarios, such as if we're synthesizing drugs, because one enantiomer will usually have some effect, while the other will often have either no effect or completely different effect. For example, with vitamin C, it's often given as a racemic mixture. Only one of the enantiomers in that mixture is actually helping you. The other one just doesn't really do anything in your body. But it's okay because at least you're getting the benefit. Some enantiomers, like thalidomide, one of the enantiomers is actually harmful, while the other is a beneficial medicine. So it's very important that we can measure those enantiomers, know what enantiomers are present, so that we can identify what we're putting in people's bodies when we're synthesizing drugs, and then how our patients will respond.